Next, we move on to our esters, which are carbonyl compounds with one alpha oxygen atom. So here's our carbonyl carbon, and here we have an oxygen atom. And then this oxygen atom has another alkyl connection. So we refer to this normally as the ether connection, while this is the carbonyl connection or carbonyl side. Okay. They are also terminal functional groups, so we'll encounter the same complexities as before. So let's name them. So again, linear esters have two parent chains. The ether side, okay, which is named like a substituent with a suffix -il. The carbonyl side, which is named as a parent with the suffix -owate. Okay, ether side ends in -il, carbonyl side ends in -owate. And esters are named in as two words. Okay, so here's an ester. There we go. On the ether side, we have a 2-carbon ethyl group. Okay, while on the carbonyl side, we have a 4-carbon butanoate group. Okay, we find two substituent methyls here and here on each side, and then we perform locant numbering, setting number 1 in this case at the carbonyl carbon, and for the other side, setting number 1 at the direct ether connection. And so when we assemble the name, we get 1-methyl ethyl, 3-methyl butanoate. Okay, so that's 2 words for our linear ester. So notice how we separate the name into 2 words. The first word being the ether side. Okay, so always the first word is the ether side, and the second word being the carbonyl side. We encounter the same situation for esters with cyclic parent chains, as it is a terminal functional group. In this case, we use the suffix carboxylate. Okay, that's the only thing that's changed. We use the suffix carboxylate. So here we have our ester. Okay, and attached to the carbonyl carbon, we have a cyclopropane. We get cyclopropane carboxylate. Attached to the ether side, we have a cyclopropyl group, so we use cyclopropyl. We don't have any substituents, so in this case, let's start locant numbering. So doing locant numbering, we set number 1 at the alpha carbon. The same for the ether side, so the direct ether connection. So assembling the name, we get cyclopropyl, cyclopropane carboxylate. Okay, so there's no locant numbering involved in the name. So that's for esters with cyclic parent chains. Here's the monosubstituted benzene ester with the name benzoate. Okay, so you can attach any alkyl group as long as you make it 2 words, alkyl space benzoate. This can be used with substitution like so. Here we have methyl, so the methyl group is right here connected to our ester. Hydroxy, 2-hydroxy, at position 2 we have our hydroxy group, benzoate. So methyl 2-hydroxy benzoate. This is also known as methyl salicylate. Okay, so one significant aspect of esters is that they are sweet-smelling compounds, which are responsible for the smell and taste of most fruits, And in this case, we have methyl salicylate, which is the active component of analgesics like Salonpas or efficacent oil. Okay, being terminal functional groups, we can also apply the same common naming schemes as aldehydes. So we use the same prefixes. In this case, we use the suffix "il" space common prefix 08. Okay, so we use a systematic prefix first, followed by "il." Okay, so we use the methyl ethyl method, but for the second name, which is the parent name, we use the common prefix with 08. So it's kind of like a hybrid name. So for example, here we have an ethyl group connected to another ethyl parent chain, but the parent chain is named using the common prefix, so we use acet. So our final name is ethyl, signifying this, and acetate, signifying the parent ester carbonyl group. Okay. Here we have pentyl formate. So we have a 1, 2, 3, 4, 5, 6, 5, 1, 2, 3, 4, 5 pentyl alkyl group, and then formate as our number of carbons. Pentyl formate, a bit of trivia, is one of the main components of the tomato taste and smell. And then here we have methyl butyrate. Here we have a methyl group, and then it's connected to a parent chain where the carbonyl carbon is connected to a 4-carbon parent chain. So here we have methyl butyrate, and if I'm not mistaken, it's the one of the flavors and scents of apple fruits. So let's work on some examples. Here we have number 1. Okay, you may have noticed that I keep using ethyl groups for the first example. I think because it's the easiest, so that's why I choose ethyl groups. So here we have our ester, which is connected to a carbonyl carbon linearly connected to another carbon. So that's 2 carbons. So we have an ethanoate. Ethanoate. Okay? And then the other side, I'll use purple, we have a methyl group. So when we assemble the name would be methyl ethanoate. Okay, methyl ethanoate. Obscured. There we go. Methyl ethanoate. Okay. Now for the next one, we have our ester here. Okay. So our carbonyl carbon is part of a parent chain that has 1, 2, and 3. Okay. So we have our propan 3-carbon OH. Our other parent chain, being the one connected directly to the ester, has 2 carbons, so we have an ethyl group. And then we have a substituent here with 1 methyl group connected to an oxygen, so it's an ether connection. So we have methoxy. And then when we add locant numbering, we start number 1 here, number 2, and number 3. So let's try assembling the name. We should get 3 methoxy propanoate. That's our second name. But the first part of our name, or the first word of our systematic name, must start with the ether connection. So we use ethyl at the start. And there's a space, emphasis, there's a space between ethyl and the parent, the other parent chain. So ethyl space 3-methoxy propanoate. Okay, let's move to number 3. Here's our ester. It has a higher priority over our ketone, so this ketone will become a substituent. Okay. This carbonyl carbon is not connected to a linear chain, rather it's connected to a cyclic chain. So in order to make this our parent chain, we must use carboxylate. Okay, as our suffix. Here we have cyclopentane. So we have cyclopentane carboxylate. Okay, so that's the parent chain of the carbonyl side. On the ether side, we have a single carbon here, methyl. Okay, and then we have a substituent here, ketone, and so we use oxo as our substituent. And then set number 1 at the alpha carbon, 1, 2, 3, 4, and 5. And so when we assemble our name, we should get, okay, methyl, or starting the name with the other side, with the ether side, we add a space, and then 2-oxo, substituent first, cyclopentane, carboxylate. Okay, so we have methyl, 2-oxo, cyclopentane, carboxylate. There we go. Okay, let's move to number 4. So here we have an ester. Okay, this carbonyl carbon is connected directly to a benzene ring. Okay, so we have a special name for that, and that is benzoate. Okay, and then here we have a group with 2 carbons directly connected to the ether connection. So this is an ethyl group. Okay, and in that ethyl group we have a substituent, methyl. Okay, so that's at the 1 position of this ether connection. So when we assemble the name, we get 1-methyl ethyl space, okay, benzoate. Okay, so here we have 1-methyl ethyl benzoate. Let's go on to number 5. Okay, here's our example with 2 esters. Okay, we have 2 esters here, and so we have a dioate. Okay, and then that dioate is spanned with 1, 2, 3, and 4 carbons, so we have a butane dioate. For our ether side, okay, we have two methyl groups. So we have dimethyl as our first word. So we have dimethyl butane dioate. Okay, so when you write it, dimethyl butane dioate. So here we go, dimethyl butane dioate. Okay, so here, number 6, we have the same, almost the same butane dioate molecule. We have a 4-carbon dioate. So here, the only difference is that we have an asymmetric ester. Okay, we have an asymmetric ester with our ether groups different from each other. So what we do is we have here a methyl group, we have here an ethyl group, and so what we do is we arrange it into 3 words with alphabetization followed. So E comes first, so we have ethyl space methyl butane dioate. So ethyl methyl butane dioate. Next, we have the anhydrides, which are dicarbonyl compounds flanking an oxygen atom. So here we have 2 carbonyl groups, and then in between them there's an oxygen atom. So there are 2 alkyl groups that can be connected to an anhydride group. Nonetheless, they are still termed as terminal functional groups, and so you may encounter the same complexities with naming terminal functional groups. A little bit of trivia: anhydrides are formed by condensing 2 carboxylic acids, a group that we will discuss after this. So let's learn how to name them. Anhydrides have 2 parent chains. Both are named with the suffix oic, OIC, and the word ends with anhydride. Symmetric anhydrides need only write one word ending in oic, followed by the word anhydride. So let's try assembling a name here. So here's the anhydride. On one side we have a 2-carbon ethanoic group, the same thing for the other side. So this is a symmetric anhydride. Doing the locant numbering, we start at the carbonyl carbon of each chain, 1, 2, and 1, 2. Assembling the name, we get ethanoic anhydride. Okay, so for a symmetric anhydride, we only need to mention one name. We don't add any di or multiplicative prefixes. So we only use one word, ethanoic anhydride. Okay, we encounter the same situation for anhydrides with cyclic parent chains, as it is a terminal functional group. In this case, we use the suffix carboxylic. Okay, we use the suffix carboxylic on the side of the parent chain with a cyclic parent chain. Okay, on the side of the anhydride. So here's our anhydride. Attached on the right hand side, we have cyclopropane. So we name it cyclopropane carboxylic. And on the left hand side, we name it ethanoic. Okay. Then with locant numbering, we name it 1, 2, 3. Okay, we give it the numbers 1, 2, and 3. And then the same for the other side. We start with the carbonyl carbon. So on the anhydride side, we start with the alpha carbon. And assembling this, we get cyclopropane carboxylic ethanoic anhydride. So this is a So this is an asymmetric anhydride, and so when we name it, the two words must be arranged in alphabetical order. And so this is a 3-word name. Here's the monosubstituted benzene anhydride with the name benzoic anhydride. This can be used with substitution like so. So here we have 2-chlorobenzoic anhydride, as this is asymmetric anhydride with 2 benzene sides. So here we have 2-chlorobenzoic anhydride. 1 word for both of the sides of the anhydride. Being terminal functional groups, we can also apply the same common naming schemes as aldehydes, and we just use the word anhydride in the end. So there are spaces in between the words. So we only use the common prefixes in this case. So for example, we have a 3-carbon anhydride, and it's symmetric 1, 2, and 3. Then we use propion, okay, propionic anhydride for this symmetric anhydride. Here we have a 1, 2, 3, 4. So this is butyric, and on one side we have formic because we only have 1 carbon, butyric formic anhydride. So for this is an asymmetric anhydride. And then here we have benzoic, okay. This side of the anhydride has a benzene ring directly connected to the carbonyl carbon. Benzoic 1, 2, 3 propionic anhydride. Okay, anhydrides have 2 sides and may close to form a cyclic anhydride. Okay, so this is different from anhydrides with a cyclic parent chain. This is a parent chain in which the carbonyl carbons are directly connected to the parent chain or are part of it, but are also enclosing itself in a ring. So this is how it looks like. When naming cyclic anhydrides, we use the suffix dioic anhydride. So in this case, whether it's symmetric or asymmetric, we use dioic anhydride. Okay, and this has its roots from the original carboxylic acid from which it came from. So it came from a dioic acid. So when they condense together and form a ring shape, this is a dioic anhydride. This is the dioic anhydride, and it has a ring system containing 6 carbons. So we have a hexane dioic anhydride. Okay, and then we have a methyl group, and then we do the numbering system, starting with number 1 at the carbonyl carbon. Notice how we don't add cyclohexane anymore. So it's already assumed that if you have a dioic anhydride, it is automatically cyclic. And so when we assemble the name, we have 2-methylhexane dioic anhydride. Cyclic anhydrides also use the same common prefixes as dialdehydes. Okay, so we use the oxal, malon, succinate, gutar prefixes in order to note how many carbons are in this anhydride. So when we use these anhydrides, they are assumed, when we use these prefixes for common anhydrides, they are assumed to be cyclic anhydrides. Okay, so we use the alcoic space anhydride. So here we have succinic anhydride because it has 1, 2, 3, and 4 carbons. So here, 4 carbon succinic anhydride. Okay, so let's do some exercises, just a couple. Okay, so here we have 2 carbons on one side Okay, and you have 2 carbons on the other. This being an oic anhydride, okay, this functional group, this is the anhydride. And then we have an identical ethan group. So this is named ethanoic anhydride. There we go. Ethanoic anhydride. Now let's go on to number 2. So we have our anhydride here. Identify first the parent functional group, oic anhydride. Okay, and on one side we have 2 carbons, so this is ethan, and on the other side it's also ethan, but we have a substituent OH at position 2, okay, 2-hydroxy ethanoic. Okay, so when we assemble the name, okay, we'll do the numbering 1 2 1 2, and so when we assemble the name, we start with 2 ethan, not 2 ethan, ethan only, ethanoic, 2-hydroxy ethanoic anhydride. Okay, and so there we go, ethanoic 2-hydroxy ethanoic anhydride. Let's erase that. Okay, let's go to the next one. So here we have an anhydride. Okay, okay, this side of the anhydride is directly connected to the part of the parent chain, which has 2 carbons, so this becomes ethanoic. This is our anhydride, and then this side, this carbonyl carbon is connected to this large cyclic system, so this system must be our parent name. So we will not use oic, rather we will use carboxylic. Okay, so it would be cyclohexane carboxylic. So when we assemble the name, considering the alphabetization, C comes before E, when we assemble the name, we must use cyclohexane carboxylic ethanoic anhydride. Okay, so cyclohexane carboxylic ethanoic anhydride. Now we go on to the next item. We have 2 carbons here. Okay, here again is our anhydride. And then we have an ethane group, ethanoic. This carbonyl carbon is connected to a benzene ring, so we have to use benzoic to refer to the entire system. Okay, so now if we assemble the name, E, okay, actually it has to be letter B. Okay, I'll do the correction there. So benzoic ethanoic anhydride. Okay, so I think this is just a correction. Benzoic comes before ethanoic. Okay, let's go to the last one, last example. Here we have a dioic anhydride. Okay, because we have a cyclic anhydride here, so it is a dioic anhydride. Okay, dioic anhydride, and it's part of a chain which has 1, 2, 3, 4, 5, 6, 7. Okay, so it is a heptane dioic anhydride. And then we have methyl groups, 2 of them, dimethyl, at positions. Okay, you can start with any direction since it's symmetrical. 1, 2, 3, 4, 5, 6, and 7. So at positions 3 and 5, our dimethyl is there. So our final name is 3, 5, dimethyl heptane dioic space anhydride. So we have 3,5-dimethyl heptane dioic anhydride. Okay, so last we move on to our highest priority neutral functional group, the carboxylic acids. These are carbonyl compounds with an alcohol group directly connected to the carbonyl carbon. So we have an OH group here directly connected to our carbonyl carbon. It is also a terminal functional group. So here are some examples: ethanoic acid, benzoic acid, cyclopentane carboxylic acid. So let's try naming them. Linear carboxylic acids are named, like all terminal functional groups, with the suffix oic acid, OIC acid. Here we have our carboxylic acid. We have 4 carbons in the longest parent chain, including the carbonyl carbon. So we have butanoic acid. We have here a methyl group. And we do locant numbering. Again, we do locant numbering to give number 1 to the carboxylic acid. Assembling the name, we get 3-methyl butanoic acid. We encounter a similar situation as in aldehydes in carboxylic acids with a cyclic parent chain. Okay, so again, this is a terminal functional group. So if we encounter this situation, we use the suffix carboxylic acid. Okay, so redundant. We use carboxylic acid as the suffix name. It's connected to a cyclic parent chain. So here's the carboxylic acid connected to a cyclic parent chain, cyclopentane. So we have cyclopentane carboxylic acid. Here we have a methyl substituent. Okay, and then with locant numbering, we set number 1 at the alpha carbon. So 1, 2, 3, at 2 position we have the methyl group. And so we get 2-methyl cyclopentane carboxylic acid. If there is a higher priority functional group than carboxylic acids, so for example, if we have a quaternary amine, okay, we can use the prefix carboxy. Okay, carboxy. Note that the carbonyl carbon is not part of the parent chain. Okay. Here is a monosubstituted benzene carboxylic acid with the name benzoic acid. This can be used with substitution like so. So here we have 2,3-dimethylphenylamino benzoic acid. So here we just have this large substituent, the 2,3-dimethylphenylamino. At the position 2, from the alpha carbon of the benzene ring, we have 2,3-dimethylphenylamino. And so, this is our benzoic acid. This is also known as mefenamic acid, which is a common anti-inflammatory drug. So, benzoic acids are common precursors for some important medicines. Being a terminal functional group, we also apply the same common naming schemes to carboxylic acids as in aldehydes. And here are the examples. So we use alcoic plus the space acid. Here's an example. Alpha-chlorocaproic acid. Having 1, 2, 3, 4, 5, 6 carbons, we use caproic acid. At the alpha position, we have a chlorine, so alpha-chlorocaproic acid. Here, in this example, we have gamma-amino butyric acid. So this is butyric acid because it has 1, 2, 3, and 4 carbons, butyr. And then at position gamma, this is alpha, beta, and gamma, we have an amino group. So it's gamma-amino butyric acid, also known as GABA, which is an important neurotransmitter in the nervous system. Okay, so the same is applicable to dicarboxylic acids, which use the prefixes oxal, malon, succinate, glutar, etc. So we just write alcoic, space, and then acid. So here we have succinic acid, since it has 1, 2, 3, and 4, 4 carbon atoms in the acid. 4 carbon atoms. This is glutaric acid with 1, 2, 3, 4, 5. Okay, glutaric acid. And here's oxalic acid with just 2 carbons and the smallest diacid possible. Succinic acid is relevant when it comes to metabolism because these are one of the intermediates in the Krebs cycle or in cellular respiration. So here, succinate. Glutaric acid is one of the backbones of common amino acids like glutamate and cooking ingredients like monosodium glutamate. Okay. So those are one of the dicarboxylic acids are very common in metabolism. Okay, so let's try some examples. Here we have 2 carbons, ethane. Here's our acid, oic acid. So we have a name, ethanoic acid. Ethanoic acid. Okay. Let's go to the next one. Here we have OH. Okay. So we have oic acid. 1, 2, 3, 4, 5 pentan oic acid. And then we have here a hydroxy group at position 1, 2, 3. 3 hydroxy pentan oic acid. That's correct. Yes. 3 hydroxy pentanoic acid. And so when you write the name, 3 hydroxy pentanoic acid. Okay. Here we have our carboxylic acid connected to our carbonyl carbon is connected to a large cyclic parent chain, and so we cannot use oic acid. In order to make this the parent chain, we have to use carboxylic acid. Okay, and here is our cyclohexane. So cyclohexane carboxylic acid. Here we have a methyl group at position 2. Okay, so this is 1, this is 2. So when we assemble the name 2-methyl cyclohexane carboxylic acid. There we go. 2-methyl cyclohexane carboxylic acid. Okay. Number 4. Here we have our carboxylic acid here. The carbonyl carbon connected to or directly connected to a benzene ring. So we have a benzoic acid. And then what we must do is perform locant numbering. Well, actually, first we identify the two substituents. We have dihydroxy at position 1, 2, 3, 4, and 5. Okay, at positions 2 and 5. Dihydroxy benzoic acid. Okay, 2,5-dihydroxy benzoic acid. Okay, let's go to the next one. Here we have 2 carboxylic acids. O, carbonyl carbon, OH. Okay, sometimes it's abbreviated as COOH when written. So take a look at abbreviation sometimes. Okay, so we have a dioic acid. Okay, dioic acid. How many carbons? 1, 2, 3, 4, and 5. Pentane dioic acid. Okay. Our substituents, we have here a dichloro. Here's our 2 chloro groups. Dichloro. And here we have an oxo group. So we do locant numbering. Can start anywhere. It's symmetric. 1, 2, 3, 4, and 5. So when you write the name, we have chloro first. Okay, C before O. 2, 4. Sorry, comma. There's a comma here. 2, 4, dichloro, 3, oxo, pentane, oh, no dash, oxopentane, dioic acid. Okay, 2, 4, dichloro, 3, oxo, pentane dioic acid. Okay, and then for number 6. Okay, here we have 3 carboxylic acids. But Since we have 3 carboxylic acids and they are not all their carbonyl carbons are not arranged in a linear manner, we can utilize the property of the carboxylic acid suffix to create a smaller parent chain. Even though it's linear, we can create this as the parent chain. Okay, this 3-carbon propane. Okay, so this is propane. I'll just write it in purple. Propane. Okay. And then we have 3 carboxylic acids, but we'll use the suffix carboxylic acid, so it will be tricarboxylic acid. And then here we have a hydroxy substituent, and then at position 1, or sorry, not here, alpha, we have to do it alpha, so 1, 2, and 3. At position 2, that is where our hydroxy lies. So when we assemble the name, we have 2 hydroxy propane 1, 2, 3. Okay, at position 1, 2, and 3 we have our tricarboxylic acid. So let's see. 2 hydroxypropane 1, 2, 3 tricarboxylic acid. So again, this is a special case wherein we have a three groups of terminal functional groups. So we must use the carboxylic acid suffix. Okay, so those are the examples for carboxylic acids and how to name them. So now we've completed learning the basic steps to naming the carbonyl compounds. We've learned about carboxylic acids, anhydrides, esters, acyl halides, amides, nitriles, aldehydes, and ketones. We've also expanded our special names for benzene derivatives. So we have benzaldehyde, benzonitrile, benzamide, benzoyl halide, benzoate, benzoic anhydride, and benzoic acid. While we've finished what is covered for a basic organic chemistry course, organic nomenclature doesn't stop here. Every possible arrangement of carbon atoms and heteroatoms have a naming system, and we can thank IUPAC for that. In any case, hopefully this helps you appreciate the diversity of organic matter. Whether you plan to study the molecules of living things or materials, I hope this becomes a launchpad for you to develop molecular advances in your fields. Until next time, goodbye.